So we introduced the function fz as consisting of the potential function and the stream function, right? And we showed that phi and psi, they do satisfy the Cauchy-Riemann equations. So fz probably is a valid incompressible (2D) irrotational flow. Okay. So this is interesting proposition. We have already seen that we have seen that phi is harmonic. But what about psi? Well, we know that ux is equal to del psi by del y and uy is equal to del psi by del x, the minus sign here. Now flow is irrotational, right? So since irrotational, our curl of the velocity field is 0, but the velocity field is 2D, so the curl is really easy to evaluate. So it basically consists of del u x by del y. This is equal to 0, which means if I put psi in here, what do we get? We have del x of minus del psi del x minus del y of del psi by del y equal to 0, which gives us the fact that the Laplacian of my stream function is also 0, and this is a consequence of, okay, so important. So this now is a consequence of the fact that we took an irrotational and 2D field. We got this, it has to be 2D because you have the stream function, but because of the irrotationality condition, you ended up getting the fact that the psi also has to be harmonic, right? So this implies psi is also harmonic. So phi and psi are both harmonic. They both satisfy the Cauchy-Riemann equations. Therefore, phi and psi are harmonic conjugates. Okay. So we have seen that the components of any analytic function are harmonic conjugates, and hence you can build up a function fz as phi plus I psi y, and this represents a valid flow field, right? So this implies that psi and phi are harmonic conjugates, and this implies that fz equal to phi plus I psi represents a valid flow field. Now whether this flow field is realistic or not is a separate question, but by choosing the right forms you can create a flow field that is a valid flow field. Whether it does apply to a real condition or not is a very separate problem. So let us see, how do you build fz? Okay, so now the question is, how do you build fz? Now see, let's take very simple case. Let's take a uniform flow, right, with components u0 and v0. So phi is going to be u0 x plus v0 y, Okay, so you can see ux is u naught, uy is v naught. So my psi now is going to be minus v naught x plus u naught y. So these are the functions that are relevant to that particular case. So fz is u naught x plus v naught y plus I times minus v naught x plus u naught y. So this actually, if you and I'm sort of skipping a quick step here, this is u naught minus I v naught x plus iy, and you can verify this. This is very easy, right? So I can replace this with z. So for so basically for uniform flow field, you will have an fz which is simply u naught minus I v naught into z. Now what I'll do is I'll just make a list of few flow fields, and let me see. Okay, so let's say the first one is the uniform stream, where you have a flow field and its components are u naught and v naught, and in this particular case you will have phi as u naught x plus v naught y, and psi is minus v naught x plus u naught y, and your fz is simply u naught minus I v naught into z. Right? We have seen, we just did this example right now. Okay, good. So now what I'll just do is I'll just state some other results, and you should go ahead and make sure that what I'm writing is correct. So for example, line source, where m is the strength of the line, which means that the flow is all flowing out of a location. Here your phi is m by 2 pi ln r, and psi is equal to m by 2 pi theta. So your fz now becomes m by 2 pi log of z minus z naught, where z naught is basically the origin. Okay, so, and I'll just quickly write what we mean by so z naught is some x naught plus I y naught. Okay, and z is equal to x plus I y for all cases. And okay, and r here, so maybe I should also explain what r is then. R is x minus x naught square plus y minus y naught square to the power half. Okay, we are running out of space here. Okay, okay, I know it's a bit too much scribbled, but hopefully, and theta is given as the tan inverse of y minus y naught x minus x naught. Okay, okay, so that was the line source. Let's see, one more is free line vortex, where we know that the vortex basically consists of concentric cylinders, right? So here my phi would be equal to some constant time by 2 pi into theta, and psi will be minus this 2 pi into r. sorry, log of r, not r, wait, should be a log, right? Yeah. Okay, so now the fz for this is minus I tau log of z minus z naught by 2 pi. Okay, and maybe we have just space for one more example. Okay, so here let's say the last example is that of a doublet. So we know how a doublet looks like, right? So this way, yeah. So this is how the doublet looks like, and phi for this, so we have done this, is some constant times sine theta by r, and phi is that same constant into cosine theta by r, and then fz here is simply c by z minus z naught. Okay, so this hopefully helps you understand how these different functions can be, the building block functions can be created. Now another important question is, given fz, how to find fluid velocities. Okay, now so let's work that out. So we are saying fz is given, and let's say you are working in the Cartesian coordinates, so then you want ux and uy. Okay, the proposition is fz, the derivative of f is this. Okay, and it's equal to, this is in the Cartesian coordinates, and if you do it in the polar coordinates, this is the answer. Okay, so the answer is already, we are giving you the answer right now, and we just want to make sure that this answer is correct. Okay, so let's see if this is truly right. So let us look at this quantity del f by del x. Okay, this is going to be equal to df by dz into del z by del x by chain rule, right? Now del f by del x is something I can indeed compute, right? So this side, okay, so let us compute del f by del x, del f by del x is 5 plus I psi del x, which gives me what? Del phi by del x plus I times del psi by del x. We should already know what this is. The first term is ux, the second term is minus uy. So for this equation, our left hand side is equal to ux minus iuy, and this is equal to df dz into dz dx. But what is z? Z is x plus iy. So this quantity is just 1, because del z by del x equal to 1. So you see, the first part of our proposition is indeed true, because del f del z is equal to ux minus I times uy. Now we also want to see whether the polar form is correct or not. Okay, now To find that, you have to express ux and uy in terms of ur, u theta. There are multiple ways of doing it. One way of doing it would be that. Now we know that in polar coordinates x equal to r cosine theta and y equal to r sine theta, right? So the first equation gives us that x dot, which is dx dt, so just for short form writing it like this, is basically r dot cosine theta minus r sine theta theta dot, and y dot was r dot sine theta minus plus r cosine theta theta dot. Now this quantity is ur, this is ux, this is uy, r theta dot is u theta. So I know that in polar coordinates ux is equal to ur cosine theta minus u theta sine theta, and uy is equal to ur sine theta plus u theta cosine theta, right? So now my del f by del z, I already know the answer is ux minus I times uy. So just go ahead and replace ux with ur, the forms that we have found, minus I ur sine theta plus u theta cosine theta. Okay, I've just replaced ux and uy, that's it. And this quantity is now going to be, since I actually know the answer, I just going to again skip a step and I'll say ur minus I u theta cosine theta minus I sine theta, and this is now equal to ur minus I u theta e to the power minus I theta. Okay, so we have proven this other proposition as well, that this is also correct, right? So both of these we have seen to be correct. Good. Okay, so I think by this time we are getting comfortable using complex potentials to represent such realistic flows, right? And we just said that we just like we are doing it with the Psi, we can use the principle of superposition to combine complex potentials and form new complex potentials. Since two functions are analytic in a domain D, then the sum is also analytic in domain D, right? So you can just start going ahead and combining various flows. And one example created by superposition is that of flow around a cylinder, a non-rotating cylinder. Cylinder of radius capital R. So let's say we combine the potential Fz. So let's take a free stream and a doublet and combine the two. Now C is a constant. This constant needs to be found. Now, do we have any important condition that we can impose? At the cylinder boundary, we want UR at R equal to capital R to be 0. Or basically psi will be 0 there. Okay. Okay. Maybe we'll just go ahead with UR. Let's see how that helps us out. So let us first write FZ. What is my FZ equal to? So my FZ is equal to UR cosine theta plus C cosine theta. We just did this numbers, right? So thankfully this functional form is already in UR sine theta in polar coordinates. So C sine theta by R. So my UR is del phi by del R. But what is my phi? This first quantity is my phi, right? So you can quickly evaluate this, which comes out to be U cosine theta minus C cosine theta. Again, this is del by del R. This is R square, right? Now the condition I want to impose is this right here. So I know the expression for UR and I want to take advantage of this particular condition right here. So to do that, what I need to do is UR at R equal to capital R is equal to 0, which for me means that U cosine theta minus C cosine theta by R square equal to 0. And this, from this you can easily see that C is equal to U R square. So the complex potential becomes Fz equal to uz plus R square by z. Okay. There are other examples too. So other examples are also possible. Other examples include the flow over the cylinder is an important one, and we'll be using that in the next class. So that's why I introduced that first. uz, for example, uz plus m by 2 pi log of z, and this is basically combining the complex potential for a uniform stream and a source. And this flow, maybe I'll just draw how it looks like. Okay, so the flow looks something like this. The flow is indicated by the blue arrows. Okay. And this is also called the flow over a Rankine half body. Okay. And I'll just leave you with one last example, and this is called flow over a Rankine oval. And here the Fz is it combines the complex potentials for a uniform stream, source and a sink. Okay, so you have uz plus m by 2 pi log z plus a minus m by 2 pi log Okay, I'm running out of space. Wait a second. Let me just move it to the next line. Minus m by 2 pi log z minus a. Okay, and please look over what this flow field looks like. Try to search and see if you can find how the flow over a Rankine oval looks like, and that will already sort of relate you to the problem that we did, which is the flow over the cylinder, right? So this is a rather important problem, flow around a non-rotating cylinder of radius r. Okay, we'll stop here for part of this recording. So we had been looking at creating examples of flows by superposition, and one of the very classical and very important such combination of potential results from the combination of a uniform stream and a doublet. And here this particular portion, this represents your uniform stream, and this represents your doublet. Now if you were to use this, I mean, you can write this in several different ways. This is also discussed, this example is also discussed in your book quite well. And if you were to look at the potential function for this, this would simply come out to ux plus ur square x square plus y square. And if you were to look at the stream function, that would come out to be uy minus ur square y by x square plus y square, right? And this is very interesting and important combination, because at psi such that x square plus y square equal to r, here this psi becomes 0, right? If you just do this math quickly, and we had imposed this condition, and hence the flow for this complex potential ends up looking something like this, where this is r, this black circle represents r equal to capital R, and then you have the doublet inside, and then you have flow outside. This flow is not very nicely created, but this is what this would look like, a flow over basically a cylinder. So this system here is very important because it sort of simulates this combination of complex potentials simulates the flow over a cylinder. And if you had to calculate, now if you were to do, let's say, try and find out the velocity distribution for this case, then we note that from Bernoulli's equation, P infinity plus rho u square by 2 is a constant, right, neglecting the gravitational portion. And usually this pressure, the change of pressure when you are, the P infinity is basically referring to flow very far away from the cylinder region, and usually this pressure at any other location is represented by a dimensionless quantity called Cp, where Cp is defined as P minus P infinity half rho u square, okay, and this is called the pressure coefficient. Now, how do you find the pressure coefficient for, okay, just a second, I'll just complete this. This is 1 minus location, the velocity at any given location by u square, right? U is, this capital U is obviously velocity at the far end. Now if you want to calculate the pressure, then you also, from Bernoulli's equation, what you need to know the velocity at any given point, right? So to find the velocity for this, you can use the set of equations that we have discussed just a little bit ago, where we had said that ur minus I u theta multiplied by, sorry, this is going to be a multiplication here, e to the power minus I theta is equal to df dz. So if you go ahead and evaluate this, what you end up finding is that my ur comes out to be u capital U 1 minus r square by small r square cosine theta, and my u theta comes out to be minus u 1 plus 1 plus capital R square by small r square into sine theta, right? So you automatically, given the form that we have found, these two equations, at small r equal to capital R, ur is automatically set to 0, right? And this is basically because we had set that condition in the beginning itself while we are defining this. And then u theta comes out to be minus u minus, sorry, so there will be this will become 2 sine theta, right? So my Cp at r equal to capital R and at any given theta is basically equal to 1 minus 4 sine square theta. And in this particular case, if you needed to find, let's say, the drag force on the cylinder, right? So now I have this cylinder. Okay, this became an oval. Just a second. Okay, yeah, now it's a circle. So if I have the my cylinder, and let's say the pressure here is P, this is R, and this angle is theta, then if I define my drag force such that it is the force in the x direction and my lift as the force in the y direction, then I can define my drag and lift by the integral of the pressure resolved into its proper component around the cylinder itself. So basically what I'm saying is that the Fd, which is the drag force, is basically nothing but the integral going from 0 to theta equal to 2 pi, so basically around the circle, minus P cosine theta, minus because the force is inward, right, into the small element over which we are doing the integration, which is r d theta, right. Similarly, Fl, the lift force, is again going to go theta varying from 0 to 2 pi minus P sine theta r d theta. Now you can either look at the pressure and you can insert the pressure from here and go ahead and evaluate these two equations, but you can also sort of easily guess that for this particular condition, if you were to introduce pressure here and integrate, what you will find is, because the pressure field, the velocity field is symmetric over the front and the back and the upper and the lower surfaces, the drag and the lift force on the cylinder will both be 0. Okay. So in this case, so either from symmetry arguments or by direct integration, you can show that both of these are going to be 0. Now this presents a paradox, because you cannot have flow over a cylinder in reality where the drag force is 0. So there is, when we had claimed that this function represents flow over a cylinder, there is definitely some problem with it, in the sense that it doesn't, one portion of it does not seem to match the reality. The fact that the potential flow here model predicts zero drag while real flows will have a non-zero drag, this is known as the D'Alembert's paradox. Okay, so D'Alembert's paradox. And this discrepancy is explained by the formation of a boundary layer and even by boundary layer separation in cases. So because at this, a real cylinder would have friction, and because of that friction there will be a boundary layer that will be created around this cylinder when there is a flow over it, and that leads to a non-symmetric that leads to a situation where you will have a drag force that is non-zero. Okay, we can see that a little bit later also. Okay, now this brings us to another important aspect that we want to learn, and this is flow around a rotating cylinder of radius r. Okay. Here what I'll do is I'll start from the opposite way. Okay, so basically there is a cylinder and this cylinder is rotating. Then the question is, what does the flow over this look like? So here I am not going to go through the entire derivation of this, but I'll just basically give out some of the broad strokes. So on the cylinder surface, okay, just like last time, on the cylinder surface, which is small r equal to capital R, we want ur at r equal to 0. U theta on the other hand, we want it to look like what you had for the so we want u theta to look something like this plus an additional term. Okay, so if this cylinder is rotating, then this u theta is the previous u theta plus another term, and here I propose a term like tau 2 pi 1 by r. Okay, and perhaps you are able to guess why I am doing that, because what's going to happen is that this will give us a net circulation around, right? So in this case it can be shown that a flow like this can be represented by Fz as uz plus cz. No, not sorry. This is okay. We had introduced c before, but we said we already know that ur square by z. Okay, so just like last time, and then we'll add one more term, I minus I tau 2 pi log of z. Okay, so basically it's a complex potential that results from a uniform stream, a doublet and a free vortex. And once you have this, then you can show that your general equation for ur, or the general value of ur here, is going to be capital U 1 minus r square by small r square cosine theta, and u theta is going to be minus u 1 plus r square. I'm just writing the results for this, okay? And these are again very simple because it's basically following the exact same logic that we had done, right, for the previous problem. So it should be rather easy for you to go ahead and work this out. And Cp for this particular case ends up becoming 1 minus 4 sine square theta plus 4 by 2 pi tau by ur sine theta minus the term tau by 2 pi 1 by ur square. And now what I want you to do is evaluate FD and FL. Okay. If you are watching this video at home, please just stop it for a few minutes and try to evaluate it. For those who are in the class, because this is the last lecture, I am just going to go ahead and give out the answer. The FD will come out to be 0 and the lift force is going to come out to be minus rho u tau. Okay. So the drag again is 0 and it is not very unexpected because of the symmetry of the velocity, but the lift is non-zero, okay, and it is related to the flow circulation, and this type of lift is also referred to as Magnus lift. Okay. So in this case I have not drawn how this looks like, but I think this is in the book. I'm not sure if the drawing for this is given or not. Yes, it is given. Okay, so the book does give out the velocities or how this looks like on page 211 in my copy. So yeah, this is the one. Okay, so you look it up.